Dear friends, there is a little bit of difference between a domestic electrician and an electromechanical engineer, because this guy made a mistake. He just played with the star delta. So all the fires, but this time it was just a dream. So let's keep it this way. The air handling unit is meant to control the temperature, the humidity, the pressure cascade and the change rates. So this is the air handling unit. As you'll see, it takes air out from the production and recirculating through a set of heat exchangers and then brings it back. Let's see now how the air circulates. What you'll see here, the air is passing from one room to another and from the AHU into the rooms. On the following video I want to show you how we can achieve this and some mistakes related to calibration. So let's look closer. This is the AHU, and what you see with red, the red represents all the area that needs to be monitored. The airflow in an air handling unit must be controlled, and for this we use automation. We use differential pressure modules, differential pressure control, which controls dampers, and also the information go to the PLC, which control variable speed drivers. You can see in this video that the DPM collect information through these two pitot tubes and send the information to the PLC, which controls the fan and send the information to the human-machine interface. I will zoom a little bit, and what you will see, the air passes by through these two tubes, which send the information to the differential pressure modules, which send the information to the PLC, and the PLC send this information to the human-machine interface. Unfortunately, sometimes when we do calibration, we calibrate only the DPM and we want to have the same value in between the calibrating tool, the DPM and the HMI, ignoring the tubes which collect data directly from the duct where the air it is moving, and this is very wrong. By calibrating only the DPM and not doing a loop calibration, we make a big mistake. Sometimes the pitot tube can get contaminated, and when we will reconnect these pitot tubes to the differential pressure module, we might have big errors in reading the pressure or the air velocity. So how can we overcome this problem? I suggest that we do a loop calibration. We will connect the differential pressure module to the pitot tubes and we use a calibrated tool to have a cross-reference in between the differential pressure module and the calibrated tool. In case this tube will be contaminated, as you will see, the differential pressure module will read an incorrect data and it will not match the data reading by the calibrated tool. DPM's reading must match the calibrated tool reading. We have to choose the right location where we fit our pitot tubes for the calibration tool, otherwise we can disturb the pitot tubes which send data to DPM. In this situation, a big enigma for me is that the PLC and the FEMS takes inputs from the same differential pressure module, so I cannot see how FEMS is independent. However, if these two tubes will be contaminated, you will clearly see that there will be a difference in between the calibrated tool reading and the pitot tube which send data to the differential pressure module. When tubes are contaminated, you will see that the DPM and the HMI and the FEMS have a different value than the calibrated tool. They read different values, because the pitot tube which send data to the calibrated tool, it is not contaminated, while the other two are, and then we have a false alarm and incorrect reading. This is the main reason why I disagree with this type of calibration, where we calibrate the DPM ignoring the pitot tubes which send data to this differential pressure module. This is an incorrect calibration. An incorrect calibration will lead to wrong pressure or air change rate reading. The fan can push more air into the ducts, and that will not only affect the air change rates and the pressure, will affect the cooling and the heating capacity, or even the moisture removing capacity. I observe with many occasions that people focusing on the heat exchangers or on the glycol temperature or the glycol flow through these heat exchangers, but we have to consider the airflow through these heat exchangers, and we don't have to push through this heat exchanger more air than it is allowed by heat exchanger specification, because they will reach a saturation point and they won't be able to do their duty. So it is very important to have an appropriate calibration, so we control the airflow and will not over exceed the maximum quantity of air that can pass by through a heat exchanger as per its specification. If you remember, I talked before about taking measurements from multiple locations. So here, if we use a bolometer, we take the measurements from inside the rooms, and then the sum of all these outlets should be equal with the measurement I'm doing now onto the supply air duct. Or if I have some losses, then I have to subtract that value. I like to take some readings from the air that is extracted from the rooms or from the fresh air intake duct. Also, I would like to take readings from the exhaust. I always want to know as much as I can about my AHU. Here you can see the heat exchangers, and you know, guys, if you push more air than the heat exchanger can support, and if you reach the saturation point, the heat exchanger won't be able to remove moisture from the air or will not heat the air enough. So every time we do this type of calibration, we have to make sure that we not calibrate only these differential pressure modules or differential control modules, or I prefer loop calibration, and also I prefer cross references with other calibrated tools, because working for pharmaceutical industry, it's very easy to understand that what you do, it is very important, and you cannot just turn the blind eye and to write things in a paper that looks good, ignoring the reality. Because when I've been employed, I've been told that we meant to save people's life. We have to have a safe product, and people try to petition the GMP with the GEP, but honestly, the air handling unit must provide the right quantity of air, and the air quality is also very important. So if we don't have the appropriate control, or if our control is not reliable, then we will not achieve the desired performance, because the control, it is nothing but technicians' eyes and ears. It's like how a microbiologist looks through a microscope to see these micro or nano entities. Me as a HVAC engineer, I need to have all these reading modules in great condition and have to be properly calibrated, because if only one it is wrong, it will be a chain of events, and I won't be able to give the appropriate answer to my managers if they will ask me what is it wrong. This year I decide to work differently. I'm going to extend my working area a little bit. I'm going to keep eye on a calibration guy. It is very important for me to make sure that what these devices will display it's real. I don't have to have massive errors, because these errors will lead to all sorts of problems. So thank you for watching this video, and I will try to put more videos, but yeah, this might be a boring video, but it is very important. You really have to make sure that your calibrated devices are properly done, and this is it. Now you can watch how the HMI look in the real world. This is just one page, and you can see some data. And can you imagine this data? It is collected from all these probes that are fitted in a duct. So if these probes gives you a wrong information on this display, you will obviously read the wrong information, and you will take action against this information. And it's like, just imagine you're a mathematician, and if you miss one number, all your equation will be corrupted. Thank you for watching my video, and I see you next time. Thank you. I will like to talk about some of this electrical work I do, or air conditioning. What you see in this picture, it is just a basic contactor. Probably most of you know what the contactor is. This is a motor, and probably you know you can connect this motor in star or delta. You can use a soft starter or a variable speed driver to run this motor. I have other videos which shows you how this motor can be wired. It is very important to study these electrical circuits before you will adventure into it. This is a programmable logic control which can control the contactor you just saw in the beginning, or this contactor. So PLC can control this contactor, and this is a HMI, human machine interface, which can show you the circuit, the way it works, so it will be easy for you to repair if a fault will occur. Now you can see here how the contactor it is connected to the programmable logic control, or to the building management control, and you will see that the contactor will only be enabled when the programmable logic control will close that little circuit onto the left hand side on the top. So when that circuit will close, the contactor will enable the motor that will turn the fan onto the right hand side. And this is a very simple circuit. Probably this motor, it's direct overload start. That's not very recommended, because you'll put a lot of stress onto the motor, into the wires, and onto the fan, and also onto the belts. People use start delta, and you will understand how start delta work if you'll watch some of my other videos. This is the start delta. You see you have a time, delay relay, and 3 contactors which allow you to run the system. This is a soft starter. It is better than a start delta. The motor will start smoother. And this is a variable speed driver. You can control the acceleration, deceleration. You can vary the speed. This is the contactor. On the top you have the control circuit. To the bottom you have the power circuit. So you have a solenoid on the top, and onto the bottom you have the power circuit. Now you see on the left hand side on the top you have a switch, and until you press that switch the contactor will not be enabled. Now I'll enable a couple of times this contactor to see what happens, and to the bottom you will see will always allow this power circuit to pass by. You'll see also a little control. That's just an auxiliary switch which allows that control to continue its journey. I'll explain to you how this works. Actually I have some other videos and you can see how this is working, but you can see even on this video you'll have a power circuit to the bottom, but the power circuit will never reach the motor until you will until the PLC on the left hand side top will close the contact, and then the contactor solenoid will be enabled. then it will create an electromagnetic force which will drive a pin down, and it will close the circuit. Then the motor will be enabled and will turn the fan. But as I said before, this is a DOL, is not used anymore. People use variable speed drivers or star delta. So please watch my other videos and learn about star delta, and this is it. Thank you for watching my video. So I will see you with some other videos. Cheers.